Hey folks, for this video we're going to talk about electric fields. And I'm going to start with this handout. Now if you're in my class, you're going to have access to this handout, so you don't need to copy everything. So what are electric fields? Okay, well, um, it's a way to imagine how two objects, a field in general, is a way to imagine how two objects can push or pull on each other even though they're not touching. Okay, so like for instance, gravitational field, how does the Earth pull on the moon or the apple or anything else for that matter? Well, we imagine that the Earth makes a gravitational field around it, and that if I put an apple in that field, the apple reacts to that field. Well, electric fields are similar. We imagine, and whether they're real or not, up for debate, but we imagine that charges make electric fields around them. And if I put another charge in that electric field, that second charge is going to react to the field created by the first charge. So the first rule here for electric fields is that the field lines are based on what force a positive test charge would experience at a particular location. Therefore, electric field lines begin on positive charges and end on negative charges. So let me explain. Look at our first picture here on the left. Let's say I were to put a little positive test charge right there. What would the big charge do to that little positive test charge? Well, it would push it. So I draw a line away. And then what if I were to put that little positive test charge there? Okay, well, this guy would push it. So the idea is a positive charge makes an electric field away from it, outward. Okay, so like so. On the other hand, I would say the second picture, I've got a negative charge. Now let's say I put a little positive test charge near that negative charge. What's this negative charge going to do to that little positive test charge? Well, that's going to pull it. So we have a field line pointing inward. And similarly, if I put a positive test charge there, I get the same thing. I get an inward pull and so on like so. So no matter where I put that positive test charge, this negative charge is going to pull it inward. Okay, so we got field lines pointing inward. If you have multiple charges in a picture, you just follow the line, the rule that electric field lines begin on positive charges and end on negative ones. So like in this picture here, our field lines would look like this. All right. So kind of like a basketball almost. And then you'd have lines going like that, and like that, and like that, and like that. And again, what do those all mean? Well, that means, let's say I were to put a negative or a positive charge right there. The force on that positive charge would be approximately, dropped the wrong way. That force on that positive charge would approximately be this way, okay, parallel to that field line right there at that spot, okay. So that's what the field lines are telling you. They're telling you what would happen if you put a positive charge there, okay. If you have two like charges, okay, then you get something like this. If I put a positive test charge in the dead center, the force on that would be 0. So here's what this looks like. The field lines kind of go like this. And you'll notice that there'll be no field lines in the dead center, okay? And then the field lines will kind of spread out like this, sort of like that, all right? And same thing up on this one here, and like that, and so on. Now, by the way, if these were two negative charges, you would get the same thing, only all the arrows would reverse and point toward the charges, okay? So again, what does this mean? This means if I were to put a little positive test charge, let's say right there, the force on that little test charge would be parallel to the field line at that point, okay? For a plane of charge, which is the next picture, the field lines start on the positive plane and go to the negative plane, and they're going to be fairly equally spaced. You get a nice even electric field there. Now at the edges, you'll get a little curving, but usually what we're going to be dealing with is near the center of this thing where the field lines are nice and constant. That means your electric field is constant. Now, if you look at the last picture here compared to the first picture, the only difference is we have more positive charge. So all you do is you draw more lines coming out of this guy. It's going to make a stronger field. Okay, so that's the only difference between the first picture and the last one, is you got more lines because you got a bigger charge making them. Which leads us to number 3 there. The number of lines leaving a positive charge or entering a negative charge is proportional to the charge. Okay, so if you have double the charge, you should have double the lines leaving. The density of the lines is proportional to the magnitude of the field at that point. In other words, the closer the field lines are, the stronger the field is. So let's say I gave you a field looks like this. Okay, so let's say here's a field, and I ask you, where is it stronger, A or B? Well, the field lines are closer together at A than they are at B. So the field at A would be stronger than the field at B. Okay, so you can tell how strong a field is by how close the field lines are to each other. At large distances from a system of charges, the field lines are equally spaced and radial if they came from a single point charge. So what that means is, let's say I had 3 positives and 2 negatives like so. Well, in this region here, you're going to have very complicated field. You're going to have a whole bunch of field lines, going like this and going like that and so on, okay? But if I step away from all this and get far away from it, okay, well, the net charge on that thing is +1. There were 3 positives and 2 negatives. So if I get far away, the field lines are just going to go like this. They're going to be equally spaced outward, again, when you get far away from it. It's going to behave as if it's a single positive point charge. There you go. And then the last one says no 2 field lines can ever cross. Why not? Well, remember what a field line represents. Go back to number 1. A field line is based on what the net force on a positive test charge would be if you put it in that location. So, imagine if we had 2 field lines crossing like this, and I put a positive test charge at that cross there where they cross. What that means is that positive test charge would feel 2 net forces, and that's a no-no, all right? You can't have 2 net forces. So field lines can never, ever cross, okay? Now, some other things about fields, okay? Let's say that I have an electric field pointing to the right. Okay, so there's our electric field. All right. We use the letter E to symbolize electric field. Okay. Well, an electric field tells you which way the force on a positive charge would be. So if I put a positive charge into that field, the force on it will be to the right. Well, what if I put a negative charge inside of that field? Well, negative charges feel a force in the opposite direction. So they would go feel a force to the left, and they would accelerate left. Okay, so it's a little like gravity turned sideways in this case, except for with gravity we only have positive mass. So if we had negative mass, like let's say your calculator had a negative mass and you let it go, instead of falling down, it would fall up, which would be kind of weird. So we don't really have an analogous negative charge in a gravitational field, at least none that we've dealt with. Now, the definition of electric field is force divided by charge. Okay. Now, the units for this, well, force is a push or pull in newtons, and charge is measured in coulombs. So the electric field strength is newtons per coulomb. Okay. And so, for instance, let me throw some numbers at you in this picture up here. Let's say E was 20 newtons per coulomb. Okay, well, if I put 1 coulomb of charge there, how much force is it going to feel? Well, if I solve for F here, F equals QE. So this 1 coulomb charge would feel 20 newtons of force. Well, what if I put a 2 coulomb charge up there? Well, then it would be 2 times 20. That charge would feel 40 newtons of force, etc. Okay, so that's what this is telling you. Now, the last thing I'll mention, the last part of this is called electric field of a point charge. And I'll do that in the next video because it's going to be an example that goes with that. So again, here's a big picture thing. We have a couple things now. We have force, which is a push or pull measured in newtons. We have charge. Okay, and then it's funny, when I ask students what is charge, I'll get all kinds of weird answers. All right. So what's your answer? What's charge? Okay, well, charge is simply an excess or a deficit of electrons. It's simply counting an electron. How do you have too many electrons? You have a negative charge. Do you have too few electrons? You have a positive charge. Do you have an equal number of electrons and protons? Then you have a neutral charge. And the reason we use Q to symbolize charge is because it stands for quantity. So that's all charge is. It's not some magic thing. It's just simply counting how many electrons you have compared to the protons. Okay. Well, now we have field. Okay, and in this case we have electric field. Okay, so I'll abbreviate that electric field, and that is newtons per coulomb. And if I ask you what's an electric field, well, that does get a little tougher to explain. It's a property of space, and it describes what forces charges will feel if I put them in that space. So if you have a problem that asks you what's an electric field, you're going to start with it's a property of a space. Okay, and then you're going to talk about the forces acting on the object if you put it in that field. All right. All right, so in our next video, we'll talk about point charges, and we'll go from there. Have a good one.